So when I was in 12th, I was told that the temperature is basically a degree of hotness or coldness, as in that's the way that it's defined for a lot of students when they first start learning anything related to thermodynamics or anything that deals with temperature. And later I realized how vague this description is and sort of like hard to deal with, right? Because sure, you can compare two bodies with different temperatures in this manner, that temperature is the degree of hotness and coldness, and so something with higher temperature should feel more hot, and you get an intuitive sense what's going on, but it's not a definition, right? Because first you'll have to define what hotness and what coldness is, but that once again depends on temperature, and so it's a circular thing. And so basically saying that temperature is the degree of hotness is not good. It's wrong. Like, this whole definition is useless because it's a circular definition. You're defining temperature in terms of temperature, so that's not making sense. So later on, when I studied a bit of thermodynamics, I was given this sort of new definition for temperature, which is that temperature can be defined as the rate of change of energy with respect to entropy at constant volume. I know a lot of words, but essentially you have these two variables called energy and entropy for some certain system, and then the derivative of energy with respect to entropy under constant volume, which is once again another variable which is very much familiar to us, and it has a good definition. So all of these, once you get to a certain level, have a definition, then you can define temperature. But the issue with this thing is that you need a definition of this variable called the entropy, and coming up with a definition of entropy took a lot of time, historically. And so till that point, what exactly was happening, like how was thermodynamics even being done, right? So usually when you go to something like Wikipedia and you look up the definition of entropy, they'll give you something like this. They'll give you it's kb natural log of omega, where omega is number of microstates and all that, and that's good. But really, can't we do it macroscopically? That's the idea. So before Boltzmann, before people really got into this statistical physics sort of thing that actually gives us a definition of entropy, how exactly was entropy even useful? Like, if you can't define something, how can you talk about it? Well, it's pretty much the same way that you can't define temperature, but you can talk about it. You can't define time, but you can talk about it, right? And so I'll be presenting some few statements which are basically from thermodynamics, and I'll be sort of proving that they are equivalent without ever having to resort to this definition. And by the end of it, we'll have a good understanding of what temperature really means, right? Okay. And also like what entropy means, because these two are very much connected. So energy is something which can be sort of easily dealt with, but temperature and entropy are new things which are hard to comprehend at times. Well, temperature isn't hard to comprehend intuitively, but it is hard to define formally, and entropy is hard in both ways. So let's just start. So first, I'll be presenting a very simple statement. Heat cannot flow from cold to hot bodies. And when I say this statement, I should be a bit more precise. This is called I think it's called the Clausius statement. So I'm just going to call it C. So C for Clausius. And what he says is that if you have two bodies, um, one at a higher temperature, so I'm going to call it TH, and one at a cold temperature, and if you connect these bodies using a diathermic wall, so a wall which lets temperature pass through it, then it's not possible that you will have temperature flowing from a cold body. Sorry, you will have heat flowing from a cold body to a hot body, and that's the whole process. So the exact statement says that there cannot exist a process whose sole result is the transfer of heat from a cold body to a hot body, or a body with a less temperature to a body with higher temperature. And so right now we don't know what this TC thing is. We can't put numbers instead of TC, but we do know that this body is colder than this body, right? And then this heat cannot flow from cold to hot. So that's the Clausius statement, and it's sort of a rule and not really a theorem or something. But let's go to the next statement, which is the Kelvin statement. So the Kelvin statement says that it's not possible that you have an engine which takes in heat from a body and then converts all of that heat, so Q in converts all of that heat to work. You cannot have a machine that does that whose sole result, so the process whose whole result is conversion of heat from some body to work, producing no heat to the surroundings. It's just not possible, right? um yeah, cool. And then we have finally the Carnot theorem, so I'm going to call it CA, which says that it's not possible that, between two reservoirs of certain temperatures, TH and TC, you have an engine with efficiency you know higher than the, I should really just calling it QH and QC and not these in out things. So it's not possible that an engine E can have an efficiency, which I'll call it as eta. So this will depend on the temperatures, obviously. So there cannot exist an engine with efficiency eta bigger than the efficiency of a reversible engine between hot and cold. So when I don't write a subscript, that just means it's for some reversible engine. And it also sort of implies that all reversible engines have the same efficiency, which is also the highest, but we'll get into that later, right? Okay, so that's sort of the thing. Yeah, what I was going to say is also this efficiency is sort of defined in this way, that it's defined as the work done upon the heat input, so QH, and that work done is just QH minus QC from conservation of energy. And so essentially we're saying that 1 minus QC upon QH must be bigger than 1 minus QC reversible upon if you had taken the same amount of heat from this. And essentially it's saying that QC is going to be bigger than QC reversible, right? So the heat that you output to this cold reservoir will always be bigger or equal to, in fact, if it is a reversible engine. So this is not possible, and what this implies is that this yeah, wait, something is wrong. It should be QH over there, fine. It should be negative. So right, so essentially we are saying that this being possible, that's the same thing as this being possible, which obviously does not happen. You cannot have an engine who which like outputs the same sort of, what was I going to say though, right? So for the same W and QH, it would output a QC which is smaller than the QC for a reversible engine. It's just not possible. So now we'll be sort of proving that the Carnot theorem thing is actually similar to both of these. It's equivalent to both of these things, the Kelvin and the Clausius statement. And once that's done, we have essentially proved that the Kelvin and Clausius statements are the same. Okay, so first let's prove that the Carnot theorem implies the Kelvin statement, which is like pretty obvious to see, because the Kelvin statement, if that were not true, then you would have an engine with efficiency 100%, right? Which obviously does not fit with the Carnot theorem. If your efficiency of the reversible heat engine is actually like less than 1, which we'll assume it is for the whole proof, right? For given TH and TC, which are distinct, right? It's not possible. So right, what was I going to say? Yes. So like the forward direction is easily proved. So now we just have to prove the reverse direction, which is that the the Kelvin statement sort of implies. Wait, no, actually this was done, right? The Kelvin statement implying Carnot thing is that's what we want to prove. So the Carnot implying Kelvin thing is already done, because if Carnot statement is true, then obviously the Kelvin statement has to be true. It cannot be that the Kelvin statement is false, right? And so the way we'll prove this implication is once again with a counter example. So suppose Kelvin, then it should not be uh, that the Carnot engine is that the Carnot. What was I going to say? Right. So suppose Kelvin statement is true, then it should not be that the Carnot statement is false, basically. And so we'll sort of try to come up with a machine that is supposedly a better engine than a reversible engine. And so let's call this machine E, right? Or let's call this M1, right? Machine M1. So it's an engine, and it's better than the reversible engine. So it's taking some QH from this reservoir at TH, and it's giving something to this guy, some QC, and then it's doing some work, right? And so we'll sort of prove that if that happens, then we can have then the Kelvin statement is basically broken, right? Okay, so now let's connect this to a perfect refrigerator, sort of, which is basically the reverse of an engine. So this was an engine, but you know that reversible processes are reversible, so we can run the engine in reverse, and we should have um, the what was I going to say? Right. So the negative of QH upon, sorry, the negative of work, right? Negative of work upon negative of QH thing. Now that should be the same. So essentially, you're saying the work done on the engine, right? Or more like the work gained by the engine, if that makes sense, upon the heat output to the hot body, right? Yeah. So now it's gonna put something. So yeah, right. And of course, it's also gonna take something from here. And so that you can sort of write this W thing as QH minus QC, right? Yes. So since we know that this engine is less efficient than M1, and this is by the way also going to be just eta. So so what you have is that yes, that this thing should be, so Q H minus QC upon whatever is the output over here, so QH dash, right? And this would just be QH dash minus of this whole thing, so minus of QH, should dash over there, not minus, minus QH plus QC. So we know that QH minus QC is the work input upon negative QH. It's like instead of that, now we just have QH dash. That thing has to be less than whatever the efficiency of this guy is, which is just QH minus QC upon QH, which is to say that QH dash has to be bigger than QH, right? Because by assumption we have that this efficiency is lower than that, so then this must happen. And if this must happen, then this quantity is bigger than QC, so you are inputting QC over here, and then you are taking something that's higher than QC, and over here as well you are taking in something that's QH and inputting something that's bigger than QH. So essentially what you have done is that the net result of one cycle of this whole combined engine would be that this TH body, it gains QH dash minus QH, and this TC body, it loses QH dash minus QH amount of energy. And that's exactly what the Kelvin statement says should not happen. So basically, if the Carnot statement is false, then that kind of means that the Kelvin statement is also false, right? Yeah. So what we kind of just prove is that not Carnot, that thing implies not Kelvin, right? And essentially that kind of proves that Kelvin implies Carnot, because if Kelvin is true, and we know it is, then that means Carnot is also true, because it cannot be that Carnot is false, because that would be Kendall's false. I mean, okay, you know how this works. Okay, so that is Kelvin being equivalent to Carnot. Now we just need to show that Carnot is also equivalent to the Clausius statement. The Clausius statement, oh sorry, I kind of proved this is the case, right? I'm writing Kelvin everywhere, it should just be Clausius. We basically have heat going from here to here, right? So it should be Clausius implies Carnot, but then that means that not Carnot implies not Clausius. So we showed the equivalence between Clausius and Carnot. Okay, or more like we just showed that Carnot implies Clausius. We didn't show, but Clausius does imply Carnot. Okay, so now we also kind of want to show that Clausius implies Carnot. No wait, we just showed that, so we want to show that Carnot implies Clausius. How does that happen now? Right, so we want to show that Carnot implies Clausius, which is the same thing as saying not Clausius implies not Carnot, right? So if you had some process which would basically like take all of the heat from one body which is colder and put it into some body which is hotter, right? If you had a machine that could in fact do something like that, so let's just call this M1, which takes in heat from this colder body and then outputs the same heat. Let's just call this thing Q for now, to a hotter body. No matter how small that heat is, if you have something like that, then that's a problem, because what we can do is that we can attach a Carnot engine, sorry, a random engine, in fact any engine, doesn't matter. So we can attach an engine which takes in Q over there, it does some work, and then so it takes in Q, and then it outputs some Q dash, which is obviously Q dash is less than Q because the work has been done. So the net process is basically that you're taking in no heat from TH basically. Okay, I think we kind of proving the Kelvin statement. That's not what we want to do. So let's just say we kind of yeah, right, okay, let's just say that this thing is Q. So the colder body does not have any sort of change in energy, and let's say this thing is Q dash, so now you just have Q dash bigger than Q, right? So this thing works just is Q dash minus Q obviously, and so now the efficiency of this whole thing is essentially, well, the work done is Q dash minus Q upon the total heat taken from TH, that's Q dash minus Q. Well, that's 1. That's wrong, right? We kind of assume that Carnot engines, so reversible Carnot engine, do not have efficiency 1, right? So the maximum efficiency is less than 1, and it is the maximum, so every efficiency would be in fact less than or equal to this, right? So every efficiency is in fact less than 1. But what we just found is that we have some engine, some machine which works as an engine which is having efficiency 1, which obviously is bigger than the reversible efficiency, and so that means that the Carnot theorem is not being satisfied. And so what we have proved is that not Clausius implies not Carnot, but that means that Carnot implies Clausius, right? The whole contrapositive thing. Yeah, so we have proved both ways. Carnot implies Clausius, at the same time Clausius implies Carnot. Yeah, prove both of these using contrapositives, and then now we are done. So we have proved the equivalence of Clausius with Carnot. What about Clausius and Kelvin? Sorry, what about Carnot and Kelvin? Well, what Kelvin's statement says is that it's not possible that you take in heat and then convert all of that to work, right? So that would have efficiency 1. So pretty much, yeah. So if the Carnot thing is not followed, then if the Kelvin statement is not followed, then obviously Carnot statement would not be followed. So the forward thing is very easy to prove. Not Kelvin implies not Carnot, because obviously you have an efficiency equal to 1 case, which is really not good. I shouldn't write like this. How do you write eta? Yeah, this. So the eta equal to 1 case, that's not good. So this implies that Carnot implies, and that was weird, but yeah, this means that Carnot implies Kelvin, right? So now we have proved that the Carnot theorem implies the Kelvin statement. We also want to prove the opposite, that is Kelvin implies Carnot, for which we want to prove that not Carnot, that would imply not Kelvin, right? So we want to create a machine, once again that's the whole idea of the construction, such that the Kelvin statement is not followed. That is, all heat from something is converted to work, right? Yeah. So notice that over here, so not this slide. So over here you had this thing going on, right? That you are taking in QH minus QH from TC and outputting the same heat to the TH thing. Now all we need to do is just sort of change this. So rather than taking in QH dash, so rather than outputting QH dash over here, what we could do is just output QH, right? And so now this would just be QH minus QH plus QC, so that's gone basically. Oh wait, okay, that's kind of wrong. You cannot do that because this is a more efficient thing, right? Yeah, but we sort of want to be doing this. So you are taking in some work, and okay, this is a bad construction idea for this. Let's come up with a new construction instead. Okay, so we want to prove that not Carnot implies not Kelvin. So once again, our usual thing, TH and TC. So the only thing we know is that there's some engine which has a higher efficiency. So just, you have an engine and it's going to do some work, and this has a higher efficiency. So you have some QH over there, QC over there, then some Carnot engine, right? So now what we have to do is just connect another Carnot engine which takes up QC, and it like gives QH over there, and some part of this work, so you have some W minus W dash thing, and then some part of this work actually goes back to this, that's W dash, right? And so now once again we can do the whole efficiency comparison thing, and we can say that well, W upon QH, that thing has to be bigger than the efficiency of this engine, which is exactly just minus W dash, because we were running in reverse, right? Reversible engines, that's what happens. This is a Carnot engine, and this is a the efficiency 1 engine. Okay, so minus W dash upon we just write it directly, W dash input upon the output to the hot, which is just QH, right? So that's essentially the thing, right? But what this implies is that W minus W dash is positive, and so the net work done because of this process is obviously positive. And notice that the cold body does not receive any energy, and so that's a problem, isn't it? Yeah. Also, this thing should not be QH. This thing really just should be yeah, it should not be QH. It should be what should I call this thing? But this should be QH, by the way. Yes. But yes, it's just something like, okay, let's actually keep it QH. Who cares? Let's just keep it QH. And from here, from the cold body, we'll take something like QH minus W dash. So yes, that's the thing. From the cold body, we'll just take QH minus W dash. Right. So now once again you compare it in the same way. You just have W dash upon QH, that should be less than W upon QH, and that implies that W minus W dash is positive. And so this work done by the combined machine is positive. But now where is this work actually coming from, right? So this TH thing is not having any loss in its energy, but this TC thing has, right? So we know that TC could also be written as just, sorry, QC can also be written as just QH minus W, but then you basically are getting QH minus W and then subtracting this QH minus W dash, but that's like, so the net effect is that you're just doing W dash minus W, so it's negative of W minus W dash, and it's W minus W dash is like positive. So the thing is that from this cold body you are taking in W minus W dash, obviously by energy conservation. In the hot body you're not taking anything, and you're converting all of that heat to work completely. So that's breaking the Kelvin statement. And so we have proved that if the Carnot statement is not followed, the Kelvin statement would also not be followed, and that is the same thing as saying that Kelvin implies Clausius. All right. Okay. So now what we have done is sort of like prove that all of these three things are equivalent. Now that does not exactly help us with defining entropy and everything, but it does give us, some sort of, like now we understand what temperature is better, essentially. Right? Yeah. And now we can, I guess, finally go to something very nice, which like, yeah, I really find this to be very nice, because I don't know, it's sort of guesswork, it's sort of so just intelligent guessing, but it gives us what we want exactly. Okay, so let's say you have some reservoirs. So let me just color this in this color. Maybe I'll color it in some slightly colder color. Maybe I'll color this in very much just no color at all. Okay, this was sort of a bad idea. Okay, so suppose you have these three bodies, and this one is at, I don't know, TH, this is at some middle temperature, and this is at a cold temperature, and you have put two Carnot engines like this. So it's taking in some QH, it's outputting some QC, and this one is taking in, so I shouldn't say QC, let's just say it's outputting some QM. This is M, by the way, and it's taking in QM and it's outputting QC over here, and the work done is obviously just QH minus QM. Over here it's just QM minus QC. Right. So you know that the efficiency will be the same, right? Let's just say these are in fact the maximum efficiency engines. So you know that efficiency is going to be same. I mean, that will obviously be the case because reversible. So there is only one efficiency possible. So you just have efficiency of the Carnot engine that's equal to, so the work done over here is just QH minus QM upon QH, which is just 1 minus Q upon QH. Yes. And that's also just equal to 1 minus, yeah, so 1 minus QC upon QM. Right. But we also know that this whole thing, in a sense, acts like an engine. And so the work done for that is just QH minus QM plus QM minus QC, which is like QH minus QC basically. So just QH minus QC and that upon QH. So that's just 1 minus QC upon QH. So we know that, no, so this probably should not be the thing. Eta is a function of T, right? So yeah, we can't just write equal to over here. So eta for, TH to TM, that's given by this thing, and then eta for TM to TC is given by this thing, and we also have eta for T, what do we call this thing? Yeah, so T H to TC directly, and that's given by 1 minus TC upon TH, sorry, QC upon QH, right? Now what we can do is sort of just do this one little thing, so just have 1 minus everything over there, and then notice that QC upon QH can be written as QC upon QM times QM upon QH. So this thing is just a product of these two. So essentially we just have 1 minus eta of THTC, that's equal to 1 minus eta of THTM, and that times of 1 minus eta of TMTC, right? Cool. That's sort of the thing. And yeah, that's the thing, obviously. And obviously we can let the efficiency be negative if your TC and TH somehow get swapped. So essentially it's just a function of two variables which can take negative values, no problem with that. And so let's just say that 1 minus eta of x to y, where x and y are temperatures, that's just some function of x and y. And so what we're essentially writing is that f of, or you know what, let's actually just take natural log of that. Yeah, that's better. So we just have f of xy is equal to f of x, right? So it's just f of x comma z plus f of z comma y, right? Yeah, this is sort of the thing. So we have some sort of functional equation, to say the least. And so this is like true for all values of z. Yeah. And so using this, we can sort of get a idea of, let's actually not take a natural log, so you can just write it using products, and that's not too bad really. So plus f of z comma y, right? This is true for all values of z, right? So what that immediately gives us is like, okay, f of x comma x is gonna be 0, which makes sense. So you cannot have an efficient engine when you're like, when both your temperatures are just the same. That would be weird. Yeah, like you're taking in heat but also giving out the exact same amount of heat. Sorry, you're taking in heat, you're doing some work and you're giving out less heat, but that's basically breaking the the Kelvin statement, right? So this is basically the Kelvin statement being enforced. Yeah, it should be multiplied, sorry. So now this is correct. Okay, so this is essentially the thing, that f of x comma y is equal to f of x comma z and then f of z comma y, right? This is true for all values of z. So a good guess is basically that, so first thing is that this is obviously true, right? We just put z equal to x over there, so it just becomes f of xy equal to f of xx times f of xy. Oh wait, this should be 1, this should be 1, sorry, because 1 minus the efficiency, right? So that's going to be 1. So obviously f of xx should be 1, which is to say that the efficiency of xx, and that should be 0, right? So that's just like one little bit of thing that we have from there. From this thing we sort of kind of want to write some sort of a differential equation or maybe something like that. So assume it's continuous in x and y, so you just have, and you have some measure of temperature. We like don't know what that measure is, but you have some measure, and so you just have natural log of f of xy is equal to the natural log of f of xz and then plus natural log of f of zy, and then let's just define these to be g. So gxy is equal to g of xz plus g of z comma y, right? Yes. And so now we can sort of differentiate this with respect to x and with respect to y, and maybe there's something nice will like come out, or with respect to z, that also works. So with respect to z, if you differentiate this, what you get like 0 is equal to g dash, I shouldn't say g dash, but more like, so with respect to the second derivative, right? So just partial g upon partial y evaluated at x comma z, right? So at this point, plus partial g upon partial x evaluated at z comma y. This is true for all values of z and x and y, right? And so this is true for all z, obviously. right? Because this does not depend on z, so this just goes to 0 obviously. And similarly, you can write a bunch of other differential equations, and then from there maybe you can get some idea of how g is going to behave and maybe solve this functional equation. But what I'm going to do is just like take the shortcut. So maybe let's just not do all of this and, you know, take a guess. Take a guess, and from this equation itself, we are actually going to take a guess, and that guess will be that this f of x comma y, maybe that could be written as something like g of x. Once again, I'm using g, but now it's a different g upon g of y, where so these two are in like fractions. So that what that will essentially do is that this whole thing would just be written as f of just g of x upon g of z, and then g of z upon g of y. So that's one good guess, because this cancels and you just get the same thing. So like I'll leave this up to you to sort of prove this happens by solving this functional equation. But essentially what we can do is we can just sort of say that your f of xy should be of this form, right? And now the thing is that x is some measure of temperature, but then so is g of x. So why not use g of x as the measure of temperature? So we can sort of say that a valid definition for temperature in that case would just be x upon y. So like f of xy equal to x upon y. Like g of x would also be some sort of a valid definition for temperature. So just let that be the definition. And then you just write f of xy equal to x upon y. And from there, it's easy to see that 1 minus eta of x over y, that's equal to x upon y, gives us eta x by y is equal to 1 minus x upon y, which is the same as saying that when you have a Carnot engine, some work done, some QH over there, some QC, whatever, which is working between, two temperatures TH and TC, you can write the efficiency as 1 minus TC upon TH. And this is like very popular. It's used in a lot of, examinations. Yeah. But right, this is sort of the, basic derivation of this thing without having to tap into any sort of other other complicated things like this equation. You don't have to type into that anymore, because you can just do this thing, right? Yes. So without using entropy or anything complicated, you can easily find the efficiency of Carnot engine. And the weird part is, like, we haven't even defined what temperature is, like what the measure of temperature is yet, and still we have somehow found this relation. It's crazy. And so it's maybe just a coincidence, but this sort of way of defining like temperature, right, this comes in handy because what we can do is, like, using this, in fact, we can have one definition of temperature. So say you fix the TH thing, right? So or maybe you fix a TC thing. So you fix the TC thing to something, let's just say 0, right? And so now you have once again an engine which is working between some temperature T and the 0 temperature. We don't know what that thing is yet, but if there's a measure of 0, you just have that. And then this equation can be written as just eta TH is equal to 1 minus TC, right? Sorry, equal to TH minus TC. Actually, let's not make it 0. Let's just make it something. So maybe like T naught. Fine. And so then this whole equation can be written as eta T to T naught. That's given by 1 minus well, TC thing is now just T naught upon TH thing is just T, right? And so from there you can have an equation for T in terms of eta. So you'll just have T naught upon T is equal to 1 minus eta, and that just means T upon T naught is equal to 1 upon 1 minus eta of T to T naught. And what this basically says is that if you know the efficiency of a Carnot engine under temperature, then you can essentially define temperature, right? So if you have a reversible engine and you know what the efficiency will be when you put it on between two reservoirs of certain temperatures which you do not know, but you do know that this temperature is constant, then you can essentially say that you have found what the temperature T should be. And so that's one way of defining temperature. It just so happens that this definition of temperature is exactly the way that temperature is defined in the Kelvin scale, right? I mean, okay, no, this isn't the definition that we are using for the Kelvin scale. It's sort of different. But what I'm saying is that the numbers match, basically, and the relations match. Another way of defining temperature is using an ideal gas. So for an ideal gas, it's a well-known fact that you just have E, which is the energy, is just um, this thing, the degrees of freedom upon 2 times PV. And so let's just say that the degrees of freedom is 3 in this case, so it's just like 3 by 2 PV, right, which is also just 3 by 2 some constant K sub B, that times the number of molecules in there, and that times of this temperature. So what that basically says is that you can define T equal to 2/3 or let's not even use the energy, because it's sort of hard to figure out what the energy is, but it is easy to figure out what this thing is, right? So we can just sort of get rid of that, and so we can sort of define the temperature as PV upon NKB. And so yes, this thing is known as the ideal gas. I mean, obviously everyone knows this. And to come to this thing, you sort of have to use this equipartition theorem and all that stuff, which already uses a definition of temperature. But you could also go the reverse way and say that for an ideal gas, you define the temperature to be PV upon NKB. And because of like the transitivity of temperature and all of the things that we have worked up now, what you can do is you have a measure of T naught, basically. And so yeah, actually you don't even need this whole definition. What you can do is that if you have a body with unknown temperature, so you don't know what the temperature is, you just put it using a diathermic wall in contact with some ideal gas. So I'm just going to draw the ideal gas, and then you change the pressure keeping the volume constant, right? Or you change the volume keeping the pressure constant, and then whenever there's thermal equilibrium between these, and that will happen, so whenever that happens, you say that they are on the same temperature. That's pretty much the definition of thermal equilibrium, by the way, right? So whenever you stop and then you say that okay, there's thermal equilibrium between them at this certain pressure and volume for the ideal gas, and then you calculate this T value, and that's the temperature for this. Easy as that, right? And this way of using thermometer, like this way of using the ideal gas as a thermometer, this gives us a definition of temperature. And it just so happens that this definition and this definition, they both match up to constants, obviously. And that's how the Kelvin scale comes to be. And of course there's a lot of other stuff which matches with this definition, like which could also be used to give definition of temperature like by itself. And so the Kelvin scale works. Essentially, that's what we're seeing. At numerous occasions, you see that the definitions with an S, they match. And so we can define the temperature using the Kelvin scale once and for all. And so yeah, that's the way the temperature should actually be defined. And I really think this T equal to partial E by partial S at constant volume thing is sort of not very useful. It is accurate and it's like cool, but it's not useful because you would need to measure energy, you would need to measure entropy, and that is hard. How do you do that, right? To measure energy, you usually rely on temperature. To measure entropy, once again, you usually rely on temperature. And so this is good in theory, but in practice, how do you even start making sense of this, right? So yeah, so now we have a good understanding of what temperature is, basically, right? And so far we haven't even talked about what entropy is, but now let's talk about it. So what happens is is that, is that for a reversible process, if okay, if I draw the PV diagram or something, maybe just like any state diagram really, you could have T or S, or you could have anything. But for a reversible process, um, for any system really, you have this sort of path going to some point and coming back at some point. So maybe you start off at A, you go to some point B, and then you come back. So throughout this, so it's a reversible process, by the way. So throughout this path, if we calculate the integration of dq upon t, right? Once again, t defined this way, and then over here as well, you determine what this value is, and then you add these up, and those should be 0, right? But now what you can do is take, so since it's like reversible, what you can do is like take the reverse path from A to B. So this was going from B to A, but now you're gonna do the opposite, and then just take the negative of this thing. So this is path 1, this is path 2, and then say that now these two are equal. It's not that the sums are equal. Okay, you know what, so let's just not write this negative over there. So now we can say that this integral and this integral are both the same, and this in fact happens for all sorts of processes basically. And so what this is saying is that this integral is a function of A and B. It's not a function of the path chosen to go from A to B. And so we'll call this function as delta S, where S is once again some property of the state A. So we'll just call this SA, and then similarly SB is just that same property for state B. So then SB minus SA is what delta S is, and this is a function of A and B. And so from there you have this concept of entropy, which is now a state variable, because we have already said that it depends on only A and B, right? So you can sort of fix A and then just move B around, and basically from there you have a definition of entropy, right? So yeah, that's how you define entropy. And it all boils down to this integral. Of course, it's supposed to be reversible processes, otherwise it doesn't work. So this integral having the same value regardless of the path. That's how you define entropy. So basically, for defining entropy, you need the temperature. That's the thing. You cannot define temperature using entropy, because you need temperature to define entropy. Unless, of course, you define entropy as this expression, which is sort of like cheating. But it's okay. It's okay. If you define it like that, then you can certainly define temperature directly. But that's not the way that this thing was done historically. Historically, you defined temperature first, or maybe more like had a semi-definition of temperature. Like you know it by its properties and not by what it is, but it's still sort of working, right? So that's what we care about. And then from that, you can come up with entropy. And from there, like Boltzmann came in and said that, oh well, entropy is somehow related to probability and all that stuff, and from there you can go the reverse way and derive temperature basically. But I like this thing better because it's more physical. But yeah, you are free to choose whichever version you like. Entropy first, temperature later, or temperature first, entropy later. For me personally, this ideal gas thing, that is the definition of temperature. I would not have any other definition. So yeah, I like this one the best. Temperature is just PV upon NKV for an ideal gas. And from there, by transitivity, you can show that, or you can define temperature for every body. That works. Yeah. So upon this, something about this equation though, I must say some stuff which has been bothering me for quite a while. So like you know that you can write ds is equal to integration of dq reversible, should be capital, who cares, dq reversible upon temperature for a path from A to B, right? Yes. Now it turns out that you have E equal to dq plus dw, right? That's the equation you usually write. And a lot of times the way that this is written is that it's dq minus p dv. So you're essentially stating that, oh well, dw has to be pdv, right? But that's wrong. That's like really wrong, because so the way that this equation is a lot of time interpreted is that this equation is true for whatever, so like whatever quasi-static process you have, this thing will be true. But that's not really true. Yeah. What is true is that dE is dq minus p external dv, basically. Yeah. And whenever I say dq, I should really just say the heat given to the body externally. It's not the heat accepted by the body. So there's some subtlety going on over there, but essentially this is the equation that you should be using and not this equation, because this is very confusing. This p over there, usually it's the same as p external because you have reversible processes, but it could be that your p external is slightly different. If only differentially it's different, right? So the equation you really should be using is this and not this. Because, and the reason I'm saying this is because there's another equation which is true, and that is dE equal to TdS minus PdV. And this equation is true all the time. So P, V, and S, and T, and E, these are all state variables for the gas, all right, not for the container or anything else. And this equation is true all the time. Okay, I'm saying gas, I should really just say system, but whatever. So the gas is the go-to example all the time. So this equation is true all the time, like for all sorts of processes. It doesn't matter if you even have a reverse, so irreversible process, right? Some weird thing that you did over there, it's okay as long as it's quasi-static. You can certainly write this because it's an equation of states, right? As long as your process is, slow enough, you can certainly, not write exactly this, but like approximately. Who am I kidding? You can actually write this thing. The only problem is like your energy being measured. That's problematic because your system has not reached equilibrium if it's not at equilibrium at every point. But if it is, then it's actually a reversible process. So then, yeah, that's a lot of like weird stuff going on over there. But you can do this. Moreover, what you can do is that you can say that delta E is equal to integration of TdS minus PdV over some path which takes you from point A to point B, right? Any path really. And then use the same thing for whatever other path you want. So, right, yeah, the equation of states is much more convenient really because it's depending on the state and not on the path. Yeah, right. And so why did I bring this up? Because if you write d equal to dq minus pdv, and you also know that this thing is true, then what you would basically have is like tds is equal to dq for any quasi-static process, which is not cool, which is certainly incorrect. Because what should happen is that ds is equal to dq reversible upon t, right? Not ds equal to dq upon t. So this equation is not valid for any process. It's only valid for a reversible one. When I say any process, I mean like any quasi-static process, but that's to be assumed obviously. So you should not write this equation. That's the thing. You should use this equation, you should use this equation, but not this. All right, cool. So that's pretty much it. I'll see you guys in the next video. Bye.